Hey, Joe.
Hi. Hey, how's my audio?
Good. Clear
Good,
on this
good,
end.
good.
Got two people here from Odin that talk here, and then just waiting on the rest of the committee.
Mhm.
Oh, there's Rachel.
Who's there in person?
I've forgot your name. Gabriel. Gabriel, and what was your name again? Ben. Ben. Hey, Rachel.
Hi, George.
Hi, Rachel.
Hi, Jeff.
Is this? I don't plan on using the chalkboard unless really necessary, but is this visible to you guys online?
Yes.
Like the handwriting is visible?
Mhm.
Okay, just in case. Looks like I'll be admitting people one by one. I couldn't figure out how to turn off the waiting room. So apologies if that kind of covers things a little bit on the shared screen. Um, just going to see if, okay, so we're still waiting on Nock and Diane. We'll give them a few minutes.
None of the Discord controls are visible to us.
None of the controls are visible to you?
Yeah, Zoom automatically hides its controls in the video.
Oh, okay, never mind. We got a lot of people joining the waiting room, so let me just admit all these. Hey, Diane.
Hi.
Thanks for coming. I think that just means we're waiting on Nock, so we'll give her a few minutes. Hey, Nock.
Hello, I'm gonna try to switch to a bigger device, but I can hear
Okay.
you for now. But you might see me drop off and join in a little bit.
Okay. I'll give it like maybe like 2 minutes before I start, just to let any stragglers in. one more minute and then I'll get started. Just so everyone's aware, this call is being recorded. Just in case that's relevant to you. Let me know if there's a problem with that or anything. Okay, I'm gonna get started. Excuse me here in the first few minutes while I admit people in the waiting room. I couldn't disable the waiting room, so sorry if that kind of hangs up a little bit at the beginning. Okay, so well, thank you everyone for coming. This is my defense of Zonotope matching and approximation for neural networks. And you know, this is a talk kind of outlining some techniques that are that can be used to some geometric techniques that can be used to study ReLU activated neural networks. And the goal of today is to kind of show you in two parts some techniques for using these polyhedral methods to improve, let's say, some neural network approximation algorithms or exact reconstruction algorithms. So I'll describe what that means here in a minute. So let's start with defining these objects. The first is, so we're going to be looking at two types of piecewise linear functions. The first, like I had just mentioned, are these ReLU networks. Here's a notation that we're using for them. And they're essentially a repeated composition of affine functions with a maximum so-called activation. Those affine functions are parameterized by a matrix and a vector B, a matrix A and a vector B. Those are called the weights and the biases. And it's also parameterized by this threshold vector T on the maximums. Those are called the ReLU activations. We can assume here that B is 0 because of those activations, because of those thresholds. It's not too hard to show that pretty much this is the same class of functions if you assume B equals 0. And we're just going to kind of throughout assume that D is our input dimension and the output dimension is 1. So these are functions to the real numbers. And the architecture here, meaning the tuple of widths of the network, would be D something, something, something 1. So D is the input, 1 is the output, and then the intermediary hidden layers have some other widths. So that's our notation for this. And then the second class of piecewise linear functions that we'll be talking about are tropical polynomials. I've got some kind of slightly odd notation to those that are unfamiliar with these objects, but I wrote it in standard as well as this tropical notation. These are essentially maxima of linear or affine functions. And you can see that on the right side. And they're parameterized. It's given by taking a finite subset of the positive or non-negative the non-negative orthant of RD. And those are the support vectors, these A's here. And then you also add on these translations CA. You take a maximum of these functions and you get a tropical polynomial. And this other notation on the left, feel free to ignore it if it's foreign to you. But if you're, say, a resident expert, maybe that's more comfortable. A great reference on this is Introduction to Tropical Geometry by McLagan and Sternfels. And I'll just note here that sometimes, and actually quite often, the vectors A are chosen to be in the integer lattice. In this case, that turned out to be not really that relevant and actually kind of a hindrance. And it's actually not too hard to show that up to kind of scaling by a constant factor, this is, you can deal with this by kind of taking rational approximations. So this isn't too bad of an assumption. And then a tropical rational function is a difference of tropical polynomials. So take two of them, take their difference. That's what we call a rational function. And I'm going to motivate this presentation by talking about some relationship between these two classes of functions. So on the left here, we have a diagram, a kind of schematic of what deep neural networks look like. And then on the right-hand side is a schematic of tropical rational functions. And there's an interesting correspondence between these two. So Zhang, Neistat, and Lim showed a way to take a neural network, one of these ReLU-activated neural networks, and write it as a tropical rational function, meaning it's a tropical rational function pointwise everywhere, and vice versa. And they give an explicit way to do this. So there's an explicit construction in either direction. It's not bijective, so it's not a per se, full correspondence, but there is a way to go in both directions. And just to kind of motivate that, let's take one direction. So the first non-trivial ReLU network you can find is a maximum. This what I've shown here is maximum of ax comma t, where a is a 1 by n vector and t is a real number. So that's a real simple ReLU network. And I'm just going to decompose the weight a into a difference of two vectors, each of which is non-negative. You can always do this. And just stick that back in and see what happens. So when you do that and you expand it out, you get two terms here, which I've underlined. And turns out that those are both tropical polynomials. They're maximum of affine linear functions with positive or non-negative coefficients. So that exhibits nu as a tropical rational function. And the idea is to kind of generalize that to deeper networks, more complicated networks. You just repeat that construction iteratively or recursively to get it for deeper networks. So that goes in kind of the right direction, taking a network and writing it as a tropical polynomial or tropical rational function. And so some observations about this correspondence, just to kind of, like I said, motivate what we're talking about today, is first, if you assume that the weights of your network are positive, or sorry, non-negative, then going in the direction I just gave the example of, constructing the rational function, you actually get a tropical polynomial. So that's interesting. And then the other direction, which I didn't give an example of, but you in the paper that I cited, you can see what they do. It's not unique, and it probably shouldn't be unique if you're kind of familiar with the way neural networks work. And in particular, going that direction does not have any tight bounds on the minimum possible depth of the resulting network. So yeah, you can do it. You can take a tropical rational function and build some weights that give you a network that's equal to it pointwise, but the depth of that network is kind of not really tightly bounded using the technique in the Zhang, Neistat, and Lim paper. So those are some observations about what they did. And based on those observations, now I'm going to talk about what this presentation and what this dissertation answers. So two questions. The first, I'm going to call the exact reconstruction problem. And this is as follows. The question is, given a convex piecewise linear function, does there exist a network nu of a given architecture? So let's say you fix your architecture to begin with, something that an architecture you care about. Does there exist such a network that's equal to a pointwise? And how unique is it? Can you characterize the kind of space of such networks? So some relevant work to this is a very, very recent preprint by Villani and Schutz showed that if F is a deep ReLU network itself, recall like F is just kind of any convex piecewise linear function. If it is a network itself, then you can find a depth 3 nu that's equal to a pointwise. So quote unquote, any deep ReLU network is shallow. Shallow is depth 3. So that was quite an interesting work. So that's recent. somewhat related by Rolnick and Cording. They showed how to determine this network, assuming it exists, given some of the outputs of F. So you don't need to know the entirety of F, you just need to know some of its outputs. And they give some ways to reconstruct those weights of the network. Okay, and then here's the second problem we'll be talking about. It's quite similar, except now we're going to loosen the requirement that pointwise equality happens everywhere. So given a piecewise linear function, how can we construct a ReLU network such that F is approximately equal to nu? We'll kind of define what approximately here would mean. But this should kind of be familiar to practitioners and theorists of machine learning. This is kind of how machine learning operates. So stochastic gradient descent, you're kind of maybe given some outputs of F, and you want to approximate F through some neural network. Another kind of maybe example would be pruning of neural networks. So you F itself is a network, some complicated neural network, and you'd like to construct a smaller one that's approximately equal to it. So these are some known techniques that exist right now for that problem. So, like I said, two questions, so two sections. We're going to talk about the first question first. So this is the exact regime. We're talking about exact quality. How do we characterize that? When does that happen? How unique is it? So I'll just kind of start off with the result. So this is what I want to show today. So let's fix d greater than 1. So this is the input dimension is 2 or more, and fix an integer n greater than d. And you're given a tropical polynomial. So let me just pause here and say, I did claim that I'd be answering this for kind of arbitrary convex functions, and tropical polynomials are not arbitrary convex functions, but let's just kind of stick with this for now. So we're given our tropical polynomial. And the problem of finding a ReLU network of architecture dn1, so that's depth 2, with one hidden layer of size n, with positive weights such that they're pointwise equal, can be solved by solving 3 geometric feasibility problems in sequence. So it's not guaranteed that such a nu will exist, but if you want to know if it exists, you can follow these 3 steps, and if each of them has a solution, then nu can be constructed explicitly. So the first step is, given a polytope associated to F, express it as a zonotope, rank n. A zonotope is a Minkowski sum of line segments, and I will be defining that precisely later on. This procedure can be done efficiently, determining if a polytope is a zonotope. If it is, go to the next step, which is solve a linear system. That's quite simple. And then finally, the third step, if that linear system has a solution, determine the feasibility of a linear program associated to this zonotope. And if that linear program has a solution, it's feasible, then you've got your answer. Nu exists, and there's an easy way to construct it. So that's the highlight. That's the pointwise equality result there that I want to talk about today. And I'll just return to this remark about what we started with, this function f. I assume that's a tropical polynomial, but actually that's not too bad of an assumption. So if I let C0PL be the space of continuous convex piecewise linear functions with a finite number of linear regions, then that is actually just the tropical polynomials plus maybe some linear functions. So the space of kind of all of these continuous convex piecewise linear functions is up to a linear term of tropical polynomials. So that's why I framed it in terms of this polynomial. Okay, so let's talk about a little bit of how the proof of this works. The main idea is to use this Legendre transform. This is defined on convex functions, and the formula is given there. And I'll explain kind of the intuition behind what it's doing if you're unfamiliar with it. It's also known as the convex dual. And it takes a convex function and gives you another convex function. And it has some interesting properties. Mainly the one that we care about is that if the Legendre transforms of two functions are equal, then actually the two functions are equal, and vice versa. That's a really, really useful property. It's kind of like the Fourier transform of convex functions in that sense, except instead of being order 4, it's order 2. So here's an example just to kind of wet your whistle if you're unfamiliar with it. So the graph of e to the x is in blue, and this Legendre transform is in red. It's not too hard of a calculation to carry out. And one thing I kind of want to point out here that's important is that the Legendre transform is not defined everywhere where the original function was defined. E to the x is defined everywhere, but the Legendre transform is only defined when x is positive because it's got a log in there. And that's not too surprising if you're familiar with like what's actually going on with this Legendre transform. What it's doing is the value of the Legendre transform at a point x is the height of the supporting hyperplane to the kind of under supporting hyperplane to the function and the associated hyperplane. So if x you think of as a normal vector to your hyperplane, then if there is a supporting hyperplane of that normal vector, then the Legendre transform's value is the translation that makes it kind of support the function. So not all hyperplanes support a function. For example, e to the x, if your hyperplane has a negative slope, it's not going to support e to the x anywhere. So that's why this Legendre transform isn't defined everywhere. That's kind of an important fact to know about these things, is that this domain is different. And we'll call the support of the Legendre transform with this notation, the set where it's finite. And kind of just by convention, where it's not defined, I'll just say it's infinity. Okay, another tool that we'll be using is the Newton polytope. Let's take a tropical rational function, tropical polynomial. Remember these things, which are maxima of affine linear functions. The Newton polytope is the convex hull of this set A, where A are these vectors that define the inner product of the affine terms. And then the lifted Newton polytope below is something quite similar, except it's in one dimension higher. And all you do is you just stick on the coefficients CA, which are the translations of those affine functions, and take the convex hull of that. It's not hard to see that the lifted Newton polytope projects down to the Newton polytope. And another piece of information we'll be using is if you fix a polytope X, we let X with this arrow on it be the upper hull of X. This is the set of faces of X whose outward normal has a non-negative last entry. A better way to think about it is if you were to look at this polytope from above, where above is like the last coordinate, then the upper hull are the faces that you'd see if you looked at it from above. So as an example, I've got here a polytope just randomly generated, and the upper hull is these pink guys. So if I were to look at this from above, all I see are the pink faces. The gray faces are not part of the upper hull. That makes sense. So it's a collection of faces. Okay. So now how are these related? How are the Legendre transform and the Newton polytope and this upper hull related? If you have a tropical polynomial, then the support of its Legendre transform is its Newton polytope. Okay. And the graph of the negative of its Legendre transform, I'm being a little bit odd here when I talk about the graph of its negative. You'll see why in a minute. But the graph of the negative of it is the upper hull of the lifted Newton polytope. So this kind of upper hull here is the graph of the negative of this convex function, f star. Importantly, the takeaway there is that the data of the Legendre transform of a tropical polynomial is exactly the same as this lifted Newton polytope, the upper hull part of it. And just as a reminder, outside of the Newton polytope, it's infinity. Its support is this Newton polytope. A really interesting kind of consequence of this is that it's a compact support. That's really nice. Okay, here's an example. Let's just take a one-dimensional tropical polynomial. I've written it in both notations here. Maximum of linear things. And the Newton polytope is the convex hull of the linear coefficients, which are 0, 1, 3, 4, and 6. And that's just the interval 0 to 6. And the lifted Newton polytope is the convex hull when I also take in these coefficients, which I'm saying are -1, 1, 2, 2, and 0. Okay, so I take those set of points, take their convex hull, I get the thing on the left. And I've highlighted in green the upper hull. And then on the right, I'm showing the graph of the Legendre transform. You notice if I were to flip it, I'd get the upper hull, the green area. So that just exhibits how the graph of the negative of the Legendre transform is the upper hull of the lifted Newton polytope. Okay, so now let's get to this main idea. I've established some tools. For a given tropical polynomial f, we would like to find the parameters of a network such that the Legendre transforms are equal. Remember, they're equal if and only if the Legendre transforms are equal. So I'm going to transfer to this convex dual case and hope that things are easier. So an equivalent way to say that is that their negative graphs coincide. That's a slightly kind of perverse way to say it, but it's true. And so the right-hand side I've already computed. F is, remember, is a tropical polynomial. I just showed what that is. That's the lifted, the upper hull of the lifted Newton polytope. So we've computed the right-hand side, and the left-hand side is unknown. We want to know what the parameters A and T are that make this true, right? We've got this network, we want to find it. So what we're going to do is compute that left-hand side in terms of A and T. And we're going to assume the architecture is of that form, this depth 2 architecture. And we will show that it is the upper hull of a zonotope. Okay, so there's where the zonotopes come in, and I'll define them next. And so once we've got that, let's say we've got our zonotope that matches this, that makes this equality happen. That zonotope is parameterized by these variables A and T. And so we can solve for those variables in a simple way through some algebraic manipulation. So that last step is pretty trivial. Okay, so now I'm going to get to zonotopes as it promised. A zonotope is the image of the unit cube under an affine linear map. So the unit cube here is IN, and the affine linear map I've expressed as a matrix applied to IN plus a translation. The generators are the columns of this matrix, and the rank is n. So remember, this can land in a lower dimension, right? D, I'm assuming, is less than n, so it's some projection of the hypercube. An equivalent way to say this is that it's the Minkowski sum of line segments. If you want to know more about zonotopes, a great reference is on zonotopes by McMullen. Really has a lot of great foundational work on it. And what are these? Well, what do they look like? Some really well-known examples are the rhombic dodecahedron, the truncated octahedron, the cube itself. Non-examples, pretty much everything else. Most things are not zonotopes. Okay, so remember, back up. So I've said this left-hand side I want to compute. So that's what I'm going to do now. I'm going to show what that is. So this is the left-hand side. So if nu is a Relu neural network with non-negative weights, then its Legendre transform is supported on a zonotope Z, and the graph over that support is the convex hull, the upper convex hull of Z bar, where Z bar is a particular zonotope that projects to this support, with an extra point Z0 on the last axis, on the Z axis. So that's my kind of claim about zonotopes, how they're related to this neural network, is that you take this Legendre transform, its graph is actually the convex hull of a zonotope with an extra point added to it. And moreover, the generators of that are parameterized in terms of these variables A and T. So here's the actual matrix Q. that corresponds to this zonotope. These are the generators of this zonotope. Okay, so we've calculated both sides of this Legendre equation. And now we just set them equal. And we've got to find a solution to that. And so the core problem is the following. This is what that means. We're given F, this tropical polynomial. We want to find a zonotope Z bar and a point Z0 such that these left and right hand sides are equal. So that's the problem. I've reduced it down to this kind of polyhedral matching problem, because it's not that I'm just showing two polyhedra are equal. I'm showing that their upper hulls are equal, which is a much looser condition. What's going on below can be whatever, it doesn't matter. All that matters what's happening is the upper hull. And that's what makes this kind of an interesting problem, is that they don't have to be exactly equal. So once we've found Z bar and Z0, we can determine these parameters A and T just by this equation here, this matrix. I've found Z bar, I know what its generators are, and I just set that generator matrix equal to this matrix, and I solve for A and T. You might be worried there's some quadratic terms there. Don't, it's separable. So it's solvable. Okay, so here's a picture. The starting data we give is F, the tropical polynomial. I've shown there the Newton polytope in gray, as well as its lift, the lifted Newton polytope in green. And what we're trying to do is find a zonotope whose upper hull matches that, basically. And that's, I'm going to kind of put this one here, this red one. This is a zonotope, the upper hull of the zonotope. And it's hard to see in 3 dimensions, but if you were to add Z0, if you were to take this to be Z0, this top point, and take the convex hull of that point with the red region, you'd get the green stuff, the upper hull of that. Okay, so that's the picture of what's going on. So here's an animation to kind of maybe give a little bit more perspective on it. So that's what we started with. Here's our data of F, and then here comes our zonotope. And that extra point, if you kind of look as it comes back down, that extra point gives you these extra lines when you add in the convex hull. And so then they match. Okay, so that's a picture of what's going on. The problem is to find the red stuff. Okay, so let's take this in dimension 1. So input dimension is 1, output dimension is 1, and there's one hidden layer. Turns out that this is a really solvable problem, and it's a nice warm-up for the general case. So I'm going to state it in the following way. If you have a tropical rational function h, now see, I've kind of gone to rational functions, but that's just because I could generalize this to rational functions. Then there exists a depth 3 Relu network such that f is equal to that network. And if it's a tropical polynomial, then it can actually be taken to be depth 2. So that second part is kind of what I've been talking about this whole time for polynomials. It just turned out to generalize really easily for rationals. Okay, so it's always solvable in dimension 1. That's cool. It's not really that complicated of a result, but it does exhibit the idea nicely. Well, a very kind of sketch of how that works is the green stuff. Remember, that's what we're given. That's the upper hull of the Newton polytope of F. In dimension 2, just looks like this green area. If I take that green thing and I reflect it in the x direction and in the y direction, I get this whole red thing. That's actually a zonotope. And so I've just constructed Z bar. If I take Z0 to be this leftmost point, their upper hulls match. So that it's really as simple as that. Dimension 1 kind of just trivially solved that way. As you go up in dimensions, it's definitely not solvable all the time. It gets way more complicated. It's similar to if you're familiar with tropical factorization, quite similar. There's factorizing tropical polynomials in dimension 1 is easy, but in dimension 2 or more, it's really not. Okay, so let's look at this dimension greater than 1. This is what I've already shown you. And I'll just go back through it again to describe these conditions that we have come up with to solve this problem. How do we get Z bar? So there's a setup. we're given a tropical polynomial, we fix an integer n, and we're looking at networks of architecture dn1. And we want to know when is their weight such that f is equal to nu pointwise, equal to our network pointwise. So the first step, express the Newton polytope of f as a zonotope of rank n, whose generators are in general position. So if you can take the Newton polytope of f and show that it's a zonotope. Now, unfortunately, like I said, most polytopes aren't zonotopes. So at this point, if you can efficiently determine this, and it's not, then you're done. It's this, just the answer is no. It's not equal to a Rayleigh network. However, if it is, then you go to the next step. So that gives you your zonotope Z. And now we want to take Z and lift it to Z bar. How do we lift it to this last dimension to make sure the upper holes match, not just the supports? Well, to do that, we're going to solve a linear system based on the generators of this zonotope and this Legendre transform, this green region. That'll give us a candidate Z bar. Now, it's not an actual Z bar yet, because there's a few extra conditions that have to be satisfied. And that's number 3, these inequalities. And if those inequalities hold, again, these are just a system of inequalities that has to hold based on the generators of Z, then that confirms our candidate Z bar. So Z downstairs is obtained by just like checking if the Newton polytope is a zonotope. Then Z bar, this last dimension lift, is obtained by a linear system and then confirmed by a linear program. The reason that this linear system and linear program are done separately rather than together is that together it's actually a quadratic program, which is less efficient to solve than a sequence of linear and then linear. So that's why I worded it that way. If they have a solution, then we can construct nu explicitly. And I showed you how, right? Like we've got Z bar, we can solve this algebraic system of equations to get A and T. Okay, so this framework has been implemented in Python. It's available online for you to check out. There's some examples in the README, and just follow those instructions. You can do this yourself. Okay, so let's move on to the next part. Remember, 2 parts. First part was exact. Second part is approximate. Now, the approximate is nicer because you can always get an answer, even if it's a really bad one. So let's look at approximation of zonotopes. And the way we're going to be doing this is through optimization, non-convex optimization. And to motivate that, let's return to our original kind of core problem that we had. Remember this boxed area, given F, find Z bar and Z0. And now we're going to replace equality of these upper holes with approximate equality. So can we make them approximately equal? And that's under some metric of polytopes. Okay, I haven't told you why that would be reasonable. Like, who says that that's going to actually give you a good pointwise estimation in the primal case? Not, this is all kind of dual shenanigans. If I were to go back to the primal, how do I know that that approximation holds in the primal? So that's a fair question to raise. And so there's the question, what is this appropriate metric to choose such that the resulting network is close to F? And the answer is the Hausdorff metric is a good one. Let's see why that is. First, let's define it. The Hausdorff metric, take P and Q subsets of metric space, non-empty. This Hausdorff metric is a distance between P and Q. And the way we compute it is it's a maximum of 2 terms. The first term is the biggest distance between a point on P and Q itself. And then the other term is vice versa, the biggest distance between a point on Q and P. So a picture is worth 1,000 words. So P is blue, Q is red. And the biggest difference, the biggest kind of distance between these two, pairwise distance between these two is shown there in black. That's a Hausdorff distance. Two polytopes are equal if and only if their Hausdorff distance is 0. Some nice properties. So that's what it is. And then just a few more auxiliary definitions on this Hausdorff stuff. If they're polytopes, I'm going to define this coarse Hausdorff distance, which is just the Hausdorff distance on their vertices. So I just consider their vertices only and just think of those as finite sets. And then the coarse Hausdorff distance is this Hausdorff distance between those finite sets. And of course, the coarse Hausdorff distance is always greater than or equal to the Hausdorff distance because the vertices are subsets of the polytope. And then I'm going to define this thing called the Hausdorff width. And it's basically just the biggest ratio that you can get between these two. And then what this does is it allows you to exchange the coarse Hausdorff width with the regular Hausdorff width at the cost of this value omega. So I can just swap these two things and stick in a factor of omega. It's always finite, this Hausdorff width, so don't worry about blowing things up. It's always greater than 1. It's actually quite an interesting intrinsic thing about polytopes. You can just ask, what is the Hausdorff width of anything? And so it's some finite number. Okay, so now I've talked about Hausdorff stuff. This is all polytopes. Now I want to talk about how does that translate into the primal setting with functions. So we're talking about piecewise linear functions. What metric does this Hausdorff metric correspond to? I'll define the following sup norm at infinity. Remember, C0PL is the space of convex continuous piecewise linear functions with a finite number of linear regions. Say that 5 times fast. And we say F infinity bar is just the limit of the supremum of a function over a ball of radius R divided by R. So you normalize by R and then take R to infinity. And what this is measuring is how asymptotically steep F is. And on piecewise linear functions, this is quite a useful metric. Oh yeah, it induces a metric between these functions. Just the distance between F and G is the norm of their difference. Okay, so here's an example. Take the simplest convex piecewise linear function we know, just a linear function. F of x is equal to eta inner product with x plus c. Then you can show, and I've shown here, that the sup norm at infinity is the norm of eta. Eta is this supporting vector of the affine function. And so if you take f and g, two such linear functions, affine functions, then the difference between them in this metric is just the difference between eta and eta prime. They're two supporting functions. So if I were to just take any LP metric, the difference between two linear functions is going to be infinite under that metric if you take your domain to be all of Rn. So that's not a super useful metric. So that's why normalizing by the radius helps. It doesn't solve every problem, but at least it solves some problems for piecewise linear guys. Okay, so here's the relationship that I've promised between the Hausdorff metric and this PL metric. So given f and g in this space of piecewise linear functions, we're going to let x sub f be the convex hull of the graph of its Legendre transform, and xg be similar for g. Then the PL metric is bounded by a factor times the Hausdorff metric between these xf and xg's. This factor gamma has to do with the Hausdorff width. Okay, so the upshot here is that if I can make the Hausdorff distance small, then I've made the PL distance small. So it's a nice bound. So if I have this control on the right-hand side, I get some control on the left. And we'll say a version of this was done independently by these authors, not quite using this Hausdorff width, but using some similar techniques on the coarse Hausdorff distance. So I'll credit them as well for kind of independently looking at this. Okay, so if maybe the last few slides were a bit much, let me just say takeaway. What does this mean? A good Hausdorff approximation of this fundamental problem, this core problem that we're trying to solve, leads to a good PL distance. And that's what we care about. That kind of confirms that the Hausdorff distance is a good thing to look at. Optimizing it is where we want to go. So the task is to find a zonotope that approximates a fixed polytope under this Hausdorff metric. And then we continue as usual. We find a good approximation, then we obtain the parameters A and T in the same way before by solving that system of equations. Okay, so now last part of this talk, how do we optimize a function over the space of polytopes? And we're optimizing the Hausdorff distance. How do we do that? Well, first, let's just define the space, the domain of optimization. Remember, a zonotope is defined by this affine map, Q x plus mu. It's the image of the unit cube under that map. And we can parameterize it that way. So we can think of the space of zonotopes as the space of pairs Q comma mu. And that's not perfectly unique though, because you can permute the columns of Q and still get the same image because the unit cube has that symmetry as well. So there's this cube symmetry. So you mod out by this permutation group Sn, and then you get a space of zonotopes, which we're going to call Zn. This thing is locally Euclidean. It's nice. It's really not very complicated. And now, like I said, we'd like to optimize the distance between a fixed polytope P. So we're kind of just in our own setting right now. We've forgotten about neural networks. We've forgotten about everything. We just want to optimize this Hausdorff distance for any given polytope P. And so I'll define this function dP. It's this distance between the Hausdorff distance between P and Z, where Z is any zonotope. That's what we want to do. So I'm just going to kind of show two main results that allow us to do that. So what do I mean by allow? Well, it's not easy to optimize a non-smooth, non-convex function. It's not easy. It's easy to show that dP is not smooth. It's also not convex. One way to show that it's not convex is show that it has multiple local minima. Maybe you have some symmetry in your polytope P, you can apply that symmetry and get different local minima. There's various arguments you can make to show it's not convex. Non-convex functions and non-smooth functions are really hard to optimize. And so I don't want to get your hopes up saying that we can always find a global optimum. That's not the case. But we can at least do some interesting work with it and get some approximate optima, some local minima. Okay, so here's the first main result that I want to explain that allows us to do that. And I know this is quite a bit of notation, but hopefully I can pick out the parts that are really important and make sure it's communicated well. So the highlight here is this function dP is locally a maximum of continuously differentiable explicit functions. Now remember, this is a function on the parameters Q and mu. Right, so it's not a function on the vertices where the vertices are the parameters. It's the function on the generators and the translation of the zonotope. So if you think of those as your inputs, it's not quite as obvious how this would be locally this way. So this is a non-trivial kind of view on what this thing is locally. Okay, so let me explain this. We're going to fix a polytope P, and then for all Z0 in this space of zonotopes outside the set of measure zero. So there are some measure zero, there's a measure zero subset of the zonotopes that this does not hold for, but that's okay. There exists a neighborhood, an open neighborhood of Z0 such that this function dPz is of this form. And so now let me explain what this form is and what each of these terms mean and how to interpret it. Well, you can see plainly it's a maximum of some things. And you've got a maximum of two terms, which are also maximum. It makes sense. That's kind of how the Hausdorff distance looked, the definition of it. What's going on inside of those is kind of the important part. I've got a delta. That delta is defined here. It's a distance between X and an affine subset W. And so if you take nothing else away from this, see that it is locally a distance between a point X and an affine subset W, where both X and W can depend on the parameters of the zonotope. So W, the subspace, can depend on the parameters. That's important to know. So this isn't some kind of trivial inner product distance function. This is some very complicated function. Phi Z is some natural bijection. You can ignore it if you don't feel comfortable with the notation. FP is the smallest face of Z containing the projection of P onto Z, and FQ is similar the other way. Affine X is the affine hull of a set X. So what I've done here is I've shown that it is a maximum of these deltas, and these deltas are a square root of an explicit bounded rational function in these parameters Q and mu, these parameters that define Z. So I've got explicit formula. I did not provide them here because it would be a mess for these deltas. And I've shown that they're the square roots of bounded rational functions, and their derivatives are, can be calculated with probably a symbolic engine like Mathematica or Python or something. So, okay, so that's the first thing. This is the local theory of DP. Second thing, the feasibility cone is a cone that I've defined that will allow us to understand how to decrease our Hausdorff distance in a guaranteed way. So let me define this. Again, fix P a polytope, and for Z in the space of zonotopes, suppose that this distance is achieved at some distinct pairs of points. Remember, like the Hausdorff distance can be achieved at multiple points if they're all exactly the same distance. So the way it's achieved at multiple points actually kind of matters. Generically, it's probably going to achieve at just one pair of points, but when it isn't, that's really interesting from an optimization perspective. It shows that you've got some constraints going on as you try to optimize, take an optimization step. Okay, so I've got these pairs of points, and for each Q, the Q I forgot to put in here, Q is the points on the zonotope Z, P are the points in P. For each Q, you can lift it to an element of the unit cube, because remember, the zonotope is a projection of the unit cube. So you lift it to a point on the cube, and I define this cone. I'm taking my entries to be matrices, comma, vectors, and I'm writing them with deltas because I want to think of these as perturbations to my parameters, some small change in my parameters. And so there's this inequality here for all these, and it's a polyhedral cone. And what does this thing tell us? Outside a set of measure 0, anything in the interior of this cone corresponds to a descent direction for the Hausdorff distance. So direction, I mean, add delta Q to delta and delta mu to mu, that gives me a descent. So more precisely, there exists an epsilon such that for all t less than epsilon, this zonotope where you kind of add these perturbations satisfies dp is less than the one where you started. Okay, so I've parameterized I've shown that the interior of this cone parameterizes descent directions for dp. If it has non-empty interior, then it's not a local minimum. That's a really nice fact to know. The converse is very complicated and isn't true, but the converse is still kind of a work in progress for me. It would be really nice if the interior was empty, then it would be a local minimum. There are some cases where that's not happening, and I'm still kind of actively trying to understand when that's true or not. But for our purposes, it's still useful to know that the interior parameterizes descent directions. Okay, so now let's put these two things together. I've defined a local theory of my Hausdorff distance, a Hausdorff function. I've defined this useful cone that parameterizes descent directions for it. Now I'm going to put them together and define a optimization scheme. And this is going to be based on the subgradient method. If you're familiar with gradient descent, this is the version of gradient descent, but for non-differentiable functions. Gradient descent obviously requires a gradient. And if you're not differentiable, you have to do something else. So this is where the Clark subdifferential comes in. It's defined as this convex hole of limiting gradients. Maybe the best way to explain this would be just a quick drawing here. The limiting gradients are just the gradients that happen as you approach a non-differentiable point. So absolute value of x. If I approach from this direction, the gradient is -1. If I approach from this direction, the gradient is +1. So the Clark subgradients is the convex hull of -1 and 1. So it's an interval -1 to 1. Okay, so the Clark subgradients is just a convex hull of limiting gradients. And it has some nice properties. If it's differentiable at a point, your function can be differentiable at some places. If it is, then the Clark subgradient is just the usual gradient, just the singleton set. If x0 is a local minimum, then 0 is contained in the Clark subgradient, but the converse is not always true. And the subgradient method, this is a widely used method in non-convex optimization, is the following. You update your value of x by subtracting off a step size, hk, times some element of this Clark subgradient. And so any application of this method needs to tell you, well, how do you choose the direction? How do you pick the element of the Clark subdifferential? And then also, how do you choose the step size? So those are the kind of, anyone that wants to use this, they have to figure those out for their particular problem. Often the step size is line search, but. Okay, so recall we showed that it's this function is locally a minimum of differentiable functions. This is where that local theory of our Hausdorff distance comes into play, because we can use that to calculate explicitly the Clark subdifferential. This lemma allows us to do that. So just take some f1 through fn be locally Lipschitz functions on a neighborhood, and they're continuously differentiable. The maximum of these functions is a new function f. Then the Clark subdifferential at a point in this neighborhood is the convex hull of the gradients of these guys. The gradients are the ones that achieve the maximum, if that makes sense. So, at a point x, f of x achieves its value at some number of functions f1 through fm. And you just look at those ones that achieve it and their gradients, and the Clark subdifferential is the convex hull of those gradients. And that's useful for us because we've already shown this. We've shown that our dp is a maximum locally, not globally, but locally a maximum of these things. So there it is. We've got the Clark subdifferential. So putting this all together, I'm going to fold in the feasible cone, the feasibility cone that parameterizes descent directions. And I'm going to define this thing called the feasible subdifferential. And all it is I take the interior of the feasible cone. Remember, that's the descent directions. Those are the good directions. And I intersect that with the Clark subdifferential. So I'm taking the descent directions that are actually steepest, if you like it. And then if this interior of this cone is empty, then just take the Clark subdifferential. Okay, so how are we going to choose an element of this subdifferential? We've kind of narrowed it down to a smaller subset of the Clark subdifferential, but we still have to choose something in there. And the way we'll do that is just the Chebyshev center. This is the most interior point, so quote unquote, of a polytope. Here's a picture of it. The Chebyshev center basically is just the one that's the point with the greatest radius that's still contained inside of your polytope. These are the things that are kind of that satisfy your inequalities the most, quote unquote. And this feasibility cone, the reason I'm doing that is that the feasibility cone, you can show the most interior points give you the best descent directions. So that's why I'm using Chebyshev center. And the step sizes, I wish I could go into details. I just don't have time for how I'm calculating those, but I'm using the geometry, the underlying geometry of what's going on with this feasible cone to calculate step sizes. Okay, so now let's do a demo. I've got an animation here of dimension 2. So we're looking at polytopes in dimension 2 of this optimization scheme that I just showed you. And here we've got blue is a randomly generated polytope P, and the red is a zonotope. And the black lines is the Hausdorff distance. Remember, I said it can be achieved at more than one point. Well, there's an example. Those black lines are the same distance. And now I'm going to run this optimization scheme. So on the bottom right there, you've got the Hausdorff distance. As I run this optimization, as you can see, the number of points that achieve the distance, the number of black lines, it tends to increase as you get closer and closer. And the jitteriness here is kind of an artifact of some of the numerics of choosing step sizes and things like that. So there we are with a decent approximation to a local minimum. The red is still a zonotope, and its Hausdorff distance is about 0.08. So just, okay, so that's the demo. And then to wrap things up here, I just want to give an application. And an application is neural network pruning. So what we're going to do is apply this kind of approximate problem that we've just solved. Remember, we rewind. Why did we do all of this optimization? Was we showed that we can approximate an arbitrary function by a depth-2 network by solving an optimization problem with zonotopes. And so backing up, let's take our function that we start with to be a neural network of some kind, maybe some really complicated deep neural network. And we want to approximate it by something depth-2. So here's how we do that. And sometimes it's called pruning. So we're going to find our tropical polynomials such that it's equal to this rational function. Remember, I said that this is always computable through that first slide, that first example I showed you with separating between non-negative weights, right? So you can always find f and g. This is a simple procedure. And what we're going to do is we're going to approximate f and g separately. So we're going to run this approximate reconstruction algorithm 2 times, one for f and one for g. And again, that corresponds to solving some zonotope optimization problem, getting a satisfactory local minimum, and the resulting network, nu, has small PL distance from f and g respectively. So now we've done our zonotope optimization, and we get 2 networks, nu f and nu g. These are 2 depth-2 networks. We're almost there. How do we combine them? Because we want to combine them into a bigger network. Well, it's not hard. You just stack their weights together. You take the parameters of f and g, which are these AF, AG, and TF, TGs, the thresholds and weights, stack them in the way I've shown. And then you add a third layer, A3, that just computes their difference, right? It just adds them one with a negative sign. And then the threshold is minus infinity for that part. So you can show that this depth-3 network, S, is equal to nu f minus nu g on the nodes. But nu f minus nu g is approximately f minus g, which is nu. Okay, so there is the connection between S and nu. And so S is this pruned neural network of depth 3, approximately equal to nu. And how well that approximation is directly depends on how good you are at zonotope optimization. If you can get really, really good at it, then your pruning gets better and better. Yeah, okay. And this optimization and pruning scheme are implemented also in Python, same repository here. You can access it online. Again, follow the README if you want to try yourself. And that's it. I appreciate your attention, and I'm open for questions. Thanks.
Thank you, George. Are there questions from the audience? I think at this time there can be questions from anyone, not just the committee.
That's simple.
Yeah.
How you can approximate sort of deep ReLU networks by like shallow ones.
Yeah.
Is there any bound on how the width of those 3 layers that you do get blows up with respect to how big the other layers fit in?
Yeah. So for the people online, in case you didn't hear it, the question was, what bounds are there on the width of this shallow network that I've constructed? Is that accurate?
Yeah.
Well, I've kind of picked the width. So the width, if you recall, is this integer n, this hidden width. That's the rank of the zonotope. So that's something that you kind of specify ahead of time.
Okay.
Now, if you choose a small n, low rank zonotope, then you're going to get a bad approximation because that's just a non-expressive zonotope. As you add rank, the more kind of flexible your zonotopes become. So you actually get to choose the width. But you got to be careful because if you choose a really small width, then it's going to be a bad approximation.
True.
Yeah. Any other questions?
Okay, so questions from the committee?
You say something about the general or position hypothesis. It wasn't clear to me when that was necessary in
Yeah.
for zonotopes and when it wasn't.
Yeah, that's a really good question. So general position of the generators of the Zonotope are used when you want to, let me pull up the relevant slide here. Here. So in this local theory of this Hausdorff distance, to write out the deltas in terms of the parameters Q and mu, you have to be able to write faces of the Zonotope as a function of the generators. So let's say like the normal vector of a given face of the Zonotope as a function of its generators. And for general position Zonotopes, that's really easy. For non-general position Zonotopes, it becomes degenerate. And so you can get some you can get some what's the word I'm looking for? Some singular values for these normal vectors, because what's happening is non-general position Zonotopes kind of collapse faces and they do some weird things. And so the differentiability of delta, I think, becomes compromised. I don't know that for sure. It just turned out to be the easiest case for me to kind of not have to worry about that by assuming general position. General position is a generic condition, though. That's kind of where this set of measure 0 comes in. So it's like a perfectly reasonable assumption for optimization problems, because if by some crazy reason you've landed at a non-general position Zonotope in your optimization scheme, you just perturb it a little bit and your general position then, and so you just continue.
Sure. Okay. So it looked to me like the hypothesis came in a little early in your writing, but I agree that it doesn't matter for optimization reasons.
Yeah, that's a good point. Let me see. This general position here for this was for the previous part of the presentation on the exact reconstruction. Is that what you're talking about?
Well, it's like in your thesis lemma 233, for example.
Oh, okay. Okay.
Yeah.
I see. Both parts, I will say, let's just say it this way. Both parts of this work, kind of the exact and the approximate reconstruction, needed that general position assumption. I think for different reasons, though. It just happened to both be, it just happened to kind of work out that they both ended up being that condition of general position.
So yeah, maybe can you say for the first part then where it was needed?
Yeah. So let me actually just pull up. I'm sorry, you get to see my ugly stuff here. Whoops. Okay. Where's it? Sorry. Okay, well, I just need to pull it up then.
We can email you your thesis.
I've got it right here. Yeah, thanks, Joe. Let's see here. Okay, so which one are you talking about, Diane?
Well, I mean, this is not the most important thing, right? I had gone.
I'm happy to answer it still, though, but
I think, sorry, I have lost my place because I'd gone forward. I think it was 233.
okay, let's see here. Let's dig into this. Okay. 2, 3, 3. Ah, here. Ah, yes. 2, 3, 3. So, this is this technical lemma, which allows you to characterize when a cubical vertex of the zonotope is an actual vertex. So a cubical vertex is a vertex is the image of a vertex of the cube. If I project the vertex of a cube down to the zonotope to get in the image, if I look at its image, it's maybe not always a vertex of the zonotope, okay? But some of them are. And so a way to characterize when a cubical vertex is a real vertex is really simple for general position zonotopes. Turns out that you need a separating hyperplane between two sets of points. For non-general position zonotopes, it becomes more complicated. And there might be a way to do it, but I just didn't investigate it.
So what's an example of a non-general position zonotope where this lemma is false?
Good question. So I've got some pictures of these guys here. Now, I'm kind of just assuming on the fly that these will not hold. It's hard to.
So I'm going to be blunt. I could not see the proof where you use this hypothesis.
Okay,
So I mean, it's not a big deal because I mean, if you're only applying it for general position, it doesn't matter if you throw in some extra hypotheses.
Yeah, you're right. It's possible that it's not used. I wrote this like 2 years ago, so it's been a minute since I've looked at this proof. Let's see here.
Maybe it's not a useful use of time.
It's also possible that it's not a required assumption. It's possible that this is true for any zonotope. I can look at that though and follow up with you on that.
Well, I think the fundamental issue here is that when you have to figure out what the generators, right? So learning the generators of the zonotope is like figuring out the weights of the network, right?
Yeah.
And what you're handed is assuming that you're compute the polytope associated with your network, then you just handed like a set of vertices, right? Yeah. So you know, okay. So suppose someone told you that yes, this was indeed like a zonotope. Then finding the generators of this zonotope, the kind of the cheapest algorithm is look for vertices that are very easy to recognize because they're kind of extreme. Like, you know, if you're imagining kind of like a if you have I guess probably if you have generators that lie in the interior of the convex hull of other guys, then when you sum up, okay, sorry, let me say it in a way that the audience can also. So if I have a say a so a zonotope is just a sum of line segments. So now suppose if I have m line segments, right? Then theoretically I could get 2 to the n vertices, right? I could get a zonotope that's 2 to the n vertices. This is the case of a cube, right? But for a lot of zonotopes, you do not get 2 to the n vertices. You get fewer, right? So that means that certain linear combinations of these vertices of the generators must lie in the interior of the zonotope, right? So now when you're handed an object that someone told you is a zonotope, if it's a cube, then that's easy to see and you find the generators. But if it's not a cube, then you would try to basically have an algorithm and try to figure out which is a set of points on this zonotope that looks like vertices of a cube, right? So that they're like summations of, you know, the correct number of guys of generators, and then this way you generate like, you know, yeah, like these are like the easy vertices you want to kind of pick out, and then you set up, as George said, like an optimization problem to solve for the points that you want. So I think this is what this generic condition is about. Yeah, like we wrote this 2 years ago. I honestly don't quite remember like if there's
It's
a
not your
easy way
defense.
to see this, but this is the intuition of it, right? So I think it might be possible to construct like an example where you have like a bad situation. The other reason is this assumption is convenient in the sense that it's very easy to prove that the program, the quadratic or the optimization program that you wrote down at the end is the correct one, right? It's just like a way to simplify the problem into that particular kind of mix of quadratic linear program. Yeah. In general, I think it is not that easy, right? If you even just determine if a polytope is a zonotope, like I don't think that's kind of has a good runtime at all.
So actually determining if a polytope is a zonotope, I believe can be achieved in O of the number of vertices times the number of edges of that polytope, depending on how, if you view that as good or bad. But the way you do that is
I think, yeah, okay. Maybe I back up. I think that depends on what is the representation of the polytope that you're given. Yeah. Yes, okay, yeah. I have a question regarding computational complexity of the second theorem that you proposed.
yes.
I think it is easier to maybe go to the slide.
Let me see here. Oh, whoops. Let's see. This one?
Yes. Is there one that defines the algorithm that you use to compute
Oh,
this?
yes. So I don't have a theorem here, but this slide defines what the algorithm is, or I guess this one.
Right. Okay. We'll take this one. Okay. Yeah. What is the complexity of just evaluating just the Hausdorff distance? I guess it's not that bad, but okay. Yeah. What's the complexity of this? You can shed some lights on it.
Sure. So the Hausdorff distance can be solved by a quadratic program. So, you know, whatever the complexity of your favorite quadratic program solver. And then in this optimization step, you've got to evaluate the Hausdorff distance, of course. And you've also got to compute things like this Chebyshev center, which is, and you know, so computing a Chebyshev center, that's a linear program. Computing this cone, I think you'll need the H representation of a cone. And you'll also need this Clark subdifferential. So of all of those, the one that dominates is the Clark subdifferential. But there is a way to, so basically the way I'm computing the Clark subdifferential, and I don't claim that this is necessarily the optimal way to do it, but the way I'm computing it is to, you calculate all possible, let's see here, these deltas, these functions, which are the local, exhibit the function locally as a maximum of these differentiable functions. These deltas, there's a bunch of them, but as you kind of vary over the whole space of zonotopes, there's only finitely many that can pop up. And so if you can calculate those deltas ahead of time, pre-compute them, and in particular, pre-compute their derivatives using a symbolic engine, say. So you, however you choose to do it, it's kind of a run, like a kind of run-up step before the optimization scheme. You can compute those derivatives symbolically. And so that symbolic calculation can then be used in the optimization step. And so you skip all of the actual derivative calculations, which can be take up a lot of floating point operations. And so it's just the evaluation on a symbolic formula that you can do. And if you assume that you do that, then the, and I show this in my thesis, then the complexity of one kind of step of this algorithm, one complete iteration is the same as the complexity of evaluating the Hausdorff distance. So you're stuck evaluating this Hausdorff distance, and it's actually the most expensive part. The trade-off, though, is that I had to do this pre-compute step, and this pre-compute step takes a lot of space complexity. So that's the trade-off.
Okay, got it. Thank you. And coming to the application then,
Yeah.
if we could go to the application slide. So what's a practical D that you think this algorithm could be run?
With my implementation, I would say D of like maybe 5 or 6, kind of pushes the limit as far as what you would want for efficiency. And that basically comes down to the Hausdorff optimization step, of course. And the intermediate width, which is N, this kind of intermediate thing, is, well, it's got to be greater than D. And that also kind of scales up the computational complexity as well. I don't have like a precise complexity off the top of my head, but from like a kind of practical perspective, what I've done with experimentation, N of like 10 has been reasonable to do.
Okay, great. Thank you.
Yeah, I guess I will clarify. The application here, unfortunately, I don't see the optimization as being at the level of kind of standard pruning techniques nearly at all. This application is kind of more just like an interesting way to view what you could do with this. So definitely I'm not making any strong claims about, say, state-of-the-art pruning or anything like that. Any other questions?
Actually, I have one more clarification question. Is there an assumption that all of your matrices in your neural networks are integer somehow, or
No.
but then, or are you, when you talk about a tropical polynomial, are you allowing real exponents then?
Yes. Yeah, and I mentioned that at the very beginning, but probably not loud enough. So let me just bring up my definition. Oh, whoops. Yeah, so here the tropical polynomial, the supporting vectors are an element of the real orthant.
Mm-hmm.
That's an assumption that was actually made by Zhang, Neistat, and Lim in developing this correspondence. And they justify it by basically saying that if you actually really want to restrict yourself to integers, you can scale it up by some factor to get rationals. And then so those rational approximations can be taken to, you can basically use rational approximations to kind of work out the difference between integer lattice and the real orthant. But yeah, that is a non-standard kind of a non-standard assumption with respect to the tropical world, as that I should have emphasized more. So
Okay, thanks, George. Oh, yeah, sorry. Go ahead, Joe.
appreciate it. I was actually just going to say, so Joe, I think that you guys can do a breakout room, right? Where you guys can confer. I'm not sure if that's something I control, or if I can just have you guys have one, maybe you, Joe, create that.
Sure, I can try to. Does anyone else know how to do this though?
I think
Diane,
you might need
Rachel,
to
or
make-
not? Yeah.
I think you might need to make Joe host.
Okay, let me make him host real quick. Oh wait, let's make him co-host.
Thank you. Okay, I'm gonna try to form a breakout room.
Okay, I will look here to see if how to do it as well, if I figured out before you.
Mm. So tried to do that. I'm not in the room myself though. So that's a little weird.
Oh. Okay, looks like they're in the room now. Okay. Well, anyone else still online? If you're not familiar with the kind of procedures of this, they're kind of conferring privately. So feel free to duck out if you want, or you can stay around until they come back. You can also ask me more questions. I can play any more animations or anything at all. Or you can just sit here.
Really good show.
Thanks, guys. Thanks for coming.
Thank you.
A little bit of baby cam for you
Hey,
guys.
Emerson.
He was mostly not in the room, but he did catch a little bit of it.
Maybe. What did he think?
I don't know. I guess we'll have to ask him later.
What was that? What'd she say?
Taylor said that he had a lot of big, deep sighs.
Okay. I think
Deep
that's a good
thoughts.
sign.
Welcome back. Can you guys hear me? Oh, it looks like.
Oh, okay, I unmuted myself. Congratulations, George. You've passed.
Thank you very much.
Okay.
And I want to
So-
thank you guys for your time. I know it's been quite a range of time zones for you guys. So your flexibility in scheduling this and taking the time to read it and all of this, it's really meant a lot. So I appreciate your time. Thank you.
Yes, thanks. And a special thanks to Rachel. So she actually is joining us a little bit ill. So
Oh.
thanks for making thanks a lot for making it, Rachel.
Yeah, sure. Congratulations, George.
Yeah, thank you so much, Rachel.
Okay. Okay. So we'll do the docu and some follow-up. Okay. Thanks, George.
Awesome. And I think I emailed you guys about this. There's the DocuSign. Then I also think Robin sent out a final draft of the dissertation. And that'll just be like for the signature page. So that like kind of like approving that version of that draft. And that draft just consists of a few typo fixes, basically spelling corrections and what have you.
Oh, do you not have the option to fix the rest of the spelling? Because
Oh, okay.
we do have a lot of typos, so it would be good if you're submitting a final version that's going to be on the UT site permanently, you might want to get out of those first.
So I have fixed all the typos, but okay.
All the typos you knew about.
Yeah, okay, and the spell check knows about.
Do you have an option to submit an update to that final draft, George?
Yes, so this one that you would be signing would, I guess technically wouldn't be uploaded to the university because they no longer require those signatures. I'm only sending that because I kind of wanted for my own purposes to have those signatures. So the official one that will be uploaded won't need signatures, so I can upload that one kind of without. But if you guys would prefer, I can still send, you can kind of refrain from signing that until I'm more sure about those typos if you like.
What's the deadline for your final upload? Just because there were some corrections and various typo fixes.
I forgot the exact date, but I'm actually not even sure if there is a deadline. So yeah, I'm open to making those changes if you guys have them.
Okay, thank you. Okay, we'll follow up by email on that. Okay, but thanks and congratulations again.
Thank you. Thank you guys so much.
Yep, congrats. Yep, bye.
Bye.
Bye.